All right, so today we're going to be looking at solving for kind of initial velocity, takeoff velocity, jumping velocity, either of those phrases, in a couple of different situations. So let's say in both of these things here, let's say I'm talking about basketball player, kangaroo, doesn't matter. I have an object, a 3 kilogram object, okay? Mass, of course, does not matter for this, for kinematics here. We don't know the takeoff velocity for either of these. It jumps up a certain height. We're going to say in the situation over here, we're going to call this situation 1. In situation 1, the jump, the object was able to jump to a height of 4 meters before falling back to the ground. So we want to know what the takeoff velocity is. We're going to say for both situations, we're on Earth. Um, in which case, we know that at the top of the jump, so the object goes upwards and then it stops momentarily, comes back down. We know that at the top of the jumps, the ending velocity, if we only consider kind of that half of it, the ending velocity up at the top, 0 meters per second, it momentarily stops. We did say both of these are on Earth, and we know that there's a downward acceleration on this object at negative 9.81 meters per second squared. And let me add that to this one as well. Negative 9.81 meters per second squared. All right. So I have 4 of our kinematic equations kind of listed right here. So in this situation, I'm looking for that initial starting velocity. I know the ending velocity. I know the acceleration. I know the distance. In this situation, they don't give me time. So out of these 4, the big question is which one involves acceleration, the 2 velocities, and distance? Because essentially that equation won't require time in it at all. So that means this equation here, it has time in it 2, 3 times depending on how you're looking at it. So I can't use that one. V squared equals V naught squared plus 2AD. There's no time in it, so that's a possibility. Put a little 1 next to it. V velocity equals starting velocity plus acceleration times time. Nope, can't use that one. And then distance is equal to the average of the velocities times time. Nope. So the only one in here that does not have time was this equation right there. So I'm even going to write that right here. V squared equals VO squared plus 2AD. All right. I'm not ready to plug in numbers just yet. If I'm looking at this, I'm looking for this V naught squared. So I'm going to try to get that by itself to begin with. So it looks like that V naught squared, that initial velocity squared, is having 2AD added to it. So the opposite of that is to subtract that from both sides. So V squared minus 2 times A times D. Now that's V squared or VO squared. In order to get V by itself, we're going to have to take the square root of both sides. So V squared minus 2AD. All right, now it looks like I'm ready to plug in some numbers. So VO, I always like to start by doing the algebra first. I think it just makes the math a lot cleaner. Square root. V squared, my ending velocity is 0. So I'm even going to ignore that part right now. So I have negative 2. So minus 2 is the same as negative 2 times negative 9.81 meters per second squared. Pretend that's a squared. Times distance we said was 4 meters. All right, so in this case, I got a negative 2 and negative 9.81. Negative times negative is positive. So really I've got 8 times 9.81. Actually, we'll just bring up the calculator. So we're going to go 2 times 9.81 times 4 equals that, but I still need to take the square root of it, so let's hit that square root button. Looks like my velocity is actually going to be 8.86. So the starting velocity, my takeoff velocity, 8.86 meters per second. That's the takeoff velocity for this object. I like to pretend it's a kangaroo, maybe a robot kangaroo. That's not important. All right, so VO, we figured it out, 8.86 meters per second. So essentially that was the starting velocity. Now we could go through and try to find time I would say that's probably not all that important right here. Um, so that's how we do that one. But oh, now let's look over at situation number 2. Let's draw a line so I know where I'm working, where I'm not. All right. So not situation number 2. It's the same 3 kilogram object. This time though, it's up in the air. Let's say half of its route. So just going to the top of the jump took 4 seconds. We're still on Earth, so acceleration is negative 9.81. At the top of the jump, that velocity, that ending velocity is still 0. So now I need an equation that uses both velocities, acceleration, and time. Okay. So I can't use distance in this one. So number 1, that's not going to work for me. Okay. Number 2 has distance in it. That's not going to work for me. This third one here, v equals vo plus at, that's a possibility. This one, d equals the average of the velocities times time, so I'm not going to use that one. All right. So it looks like the equation I'm using, final velocity equals starting velocity plus acceleration times time, and that's not a square, that's that 2 I added to it. All right, so now I'm still looking for VO, so I need to get that by itself again. So in this case, VO is equal to velocity minus acceleration times time. All right, so now I can plug in some numbers. V once again is 0. 0 we're subtracting, negative 9.81. Double check that I'm doing this right. Looks like it. You go away, calculator. All right, so 9.81 meters per second squared times time, which we said was 4 seconds. All right, and I can kind of see where the seconds up top here will cancel that square there. So really VO is equal to subtracting a negative, same as adding a positive. Those cancel. That's not right. It's more like negative times a negative is a positive. 9.81 meters per second squared times 4 seconds. Seconds cancels that. All right, 9.84 times 9.81 times 4. Bring this over. In this case, our starting velocity was 39.24 seconds, or sorry, 39.24 meters per second. Okay, that was my takeoff velocity. We are about, 4.5 times more than this. And really, if you think about it, if you were to jump up and it took 4 seconds to get to the height of your jump, you're either on the moon or you are going to go a very, very long distance because you're going to be in the air for a long time. Um, and so in order to get that, considering, we have this pretty big acceleration working against that starting velocity, that kind of makes sense. So really with the kinematic equations, when we're using them, it's all about trying to figure out what were we given and then which equation uses those variables. Essentially, which equation doesn't have the value we don't have, but does have the one that we're looking for, I guess is the very confusing way I'm going to word that. So that's kinematic equations. I hope that helps out. Otherwise, good luck.